There's no doubt that we need our organs to survive and reproduce. They perform vital functions such as providing our cells with nutrients, getting rid of toxic waste products, and coordinate every action we make until they don't. Organ failure occurs when a major organ stops working and causes the patient to rely on very strong medicines and machines for survival. Thankfully, a patient can undergo an organ transplant, which can extend life expectancy and improve life quality. So when your organ works very poorly or even fails, you may join the organ transplant waiting list. But as our demand far exceeds our supply of suitable organs, we're faced with a crisis. The organ shortage crisis. And this crisis is getting worse every single year. What if we no longer had to harvest organs from humans? And what if we find new ways to fabricate them, maybe even in a lab? Similar to 3D printing, bioprinting is an additive manufacturing technique in which 3D objects can be built from computer-aided design models. But unlike 3D printing, bioprinters work with cells and biomaterials, creating organ-like structures that allow living cells to multiply and grow. The goal of bioprinting is to ultimately create anatomically correct biological structures for clinical and commercial applications. The bioprinting process involves preparation, printing, maturation, and application, but it can be summarized in 3 basic steps. First, pre-bioprinting. From CT and MRI scans, a digital file can be created for the bioprinter to read. At this step, researchers prepare cells and mix them with bioinks to ensure that tissue model can be successfully printed. Next, we have the actual printing, where researchers load cells and bioinks into cartridges, and we can have multiple print heads to print the desired construct. Developing different types of tissues requires researchers to use different types of bioinks, cells, and equipments. Finally, we have post-bioprinting, where printed parts can undergo chemical or mechanical stimulation to form stable structures. Afterwards, our printed models are placed into incubators or bioreactors for cultivation. But a major challenge to bioprinting is in formulating the right bioinks. To ensure biologically correct functionality, an ideal bioink should possess the mechanical, rheological, and biological properties of the target tissues. Think of designing bioinks like using a soundboard. There are so many switches, dials, and buttons that influence the sound produced. You have to experiment, adjust, try until you find the desired result. But it's nearly impossible to perform the individual experiments for an infinite number of cases with different bioprinting conditions and bioink formulations. But in the bioink, we still want to understand the environmental stimuli and forces applied during printing and their impact on the viability and biological performance of a tissue. And for bioprinting to have wider applications, the bioinks need to be standardized. New models and standards need to be developed to compare bioprinting processes, evaluate the properties of different biomaterials, and to standardize the use of bioinks. So while significant strides have been made in the field of bioprinting since 2003, the commercial availability and clinical application of bioprinting has been limited by the lack of suitable bioinks. And here comes Vitality, a bioink research and development platform dedicated to evaluating the biological function of printed constructs with mathematical and analytical models, specifically decision tree classifiers. We're pioneering predictive tissue engineering to increase the probability of successful and viable constructs from bioinks. We're leveraging machine learning to predict the role of biomaterials in biological functions and processes, specifically angiogenesis, which is the formation of new blood vessels from existing ones. If we want to print vascular networks that allow for the constant flow of oxygen and nutrients inside bioprinted tissues, we need to provide a 3D environment that is conducive to angiogenesis. So Vitality has a 4-step pipeline to predict the bioinks that will stimulate angiogenesis in printed vascular tissues. The first steps consists of formulating bioinks with biomaterials at varying concentrations. We're looking at collagen, elastin, fibrin, agarose, alginate, matrigel, and even more for their unique advantages and limitations in developing vascular tissues. Our second step is printing the vascular constructs. For each bioink that we develop in the previous step, we're printing a vascularized tissue using extrusion-based bioprinting. Each developed tissue will have distinct properties and processes, and will help us evaluate which bioinks most promote angiogenesis. At the third step, we're determining the properties of the bioprinted constructs. We'll be looking at tube formation and cellular proliferation and migration. If we want to quantitatively analyze the angiogenic response of tissues, we can count the number of vessels that are developed and measure the length, caliber, or density of these vessels. To measure cell growth, we can quantitatively observe cell behavior and cell proliferation in these tissues. Vitality will run many assays and tests to identify pro and anti-angiogenic agents and factors in the printed constructs. Our fourth step involves training our machine learning models on the quantitative data we had just obtained. Vitality uses decision tree classifiers, which are simple, but are embraced for their unique, high interpretability and ability to run unlimited data. Our model would be able to analyze the impact of certain biomaterials on biological processes. At first, we're looking at angiogenesis, but eventually, Vitality's model will reveal the composition of bioinks that promote a multitude of cellular processes. So seeing as bioprinting was only invented in 2003, it is still in its infancy. Leveraging this technology for organs and tissues will be revolutionary. It has the potential to make medical care faster, more effective, and more personalized. By combating the organ shortage crisis, we'll be saving millions of lives, both at low risk and at low cost. At the forefront of bioink development, Vitality is contributing to the advancement of bioprinting and bringing the reality of lab-grown organs closer to fruition.